Thank you very much. So I'm Ansar Calloo from from CEA, sorry. Bad habit. Today I'm going to talk to you about parallel sweep algorithms on hexagonal grids for CPUs and GPUs. So this work is mainly done by my PhD student, who's Gabriel, who could not be here today. And so if you like it, it's thanks to him. And if not, I'm a bad presenter. So just a quick word about what we're trying to do. At CEA, we're trying to work on a new software stack for solving the Boltzmann equation, which is basically the equation which is used to represent neutron transport in reactor physics problems. So we are working on how to do this and do this correctly with a new whole software around the things to do multiphysics calculation, etc. When we look at multiphysics calculations with these things, we see that when we do, for instance, coupling with neutronics, thermohydraulics, etc., these are highly parametric problems. And in these problems, when you do, we see that neutron transport is still very important into that. So I'm not going to talk too much, not at all, in fact, in this talk about Cartesian grids, because lots of things have been done on that thing. I'm going to focus in this talk on hexagonal grids only. So the goal is to design and develop an efficient neutronic solver for structured geometries, Cartesian and hexagonal ones. Again, just one thing to put the physical setting here. The neutron flux, which is the unknown we are solving for, is a 6D problem. It depends on 3 on space, 2 for the direction, and 1 for the energy. So the way we usually do this, we have that equation which is down there. It depends on, so we take the energy variable, we make it a mesh, a 1D mesh, and they're actually called groups, whatever, we don't care. And for directions, we actually do something called discrete ordinates, where we put different points on the unit sphere, and we're going to solve for each of those points. And then in the term, which is on the right-hand side, the source term, this is where we would have neutrons scattering from one energy or from one position or from one direction to another one. And it will contribute, this is the coupling which happens in the term on the right. So we solve this problem through nested iterative algorithms, be it power iteration, Gauss-Seidel, Jacobi, Richardson, etc. The way we solve this problem, actually, if we look into space, for a given direction here, omega d, you would start by solving the problem for cell 0, which is on the far right here. Once you've solved you've inverted the transport operator in 0, you can solve the problem. You have an outgoing flux for cells 1 and 3, and for cell 4, and which means that you can compute cells 1 and 3. You can't compute 4 yet, because it depends also from the outgoing flux from 3 and 1. So you would do this in a wavefront manner, moving from one wavefront to another as you progress into the problem. So you can see that this problem is very complicated to expose parallelism on this, and we have to do efficient parallel sweeping to expose more and more parallelism to be able to tackle GPU problems. Also, what you can see from this is that this problem, this sweep problem, is actually a DAG. Okay, so we can actually take lots of things which have been done into DAGs and put into those things. Some port of the transport operator to actually more parallel architectures have been done at LANL with the Snap proxy app and with Crypco, which is from Livermore. But both of these proxy apps actually work on a scheme which is called a diamond difference scheme, where we only have 1 degree of freedom per cell. In our case, we're going to look at discontinuous Galerkin problems, where you actually have a small system. It's a dense matrix, which you're going to invert locally each time as you move on. So we're not building a huge system where we can actually put Betsy or whatever on it afterwards. We are moving with a wavefront manner, and we're going to solve it locally. Now, this wavefront algorithm, okay, we've been looking at it from the neutronics point of view, but in fact, if we look at literature, one thing I wanted to show here is that it's a problem which exists in neutronics, okay, from far back till in the 60s, But then it has also been put as a parallel pattern which exists. For instance, I found that funny to see people like Lamport who actually work on that problem, and he actually called it a hyperplane method, which is a way of moving with your wavefronts. TBB also talks about an implementation about wavefront parallel processing for this thing. So we're going to see a little bit what we've done for that. Since everyone writes proxy apps, we've written another proxy app which is called Donut. It's for Discrete Ordinates NeUtron Transport. It's a few thousand lines, which is totally written from scratch with Cocos. We've let the real app on the side. We actually have implemented sweep kernels in sequential with SIMD, with parallel feeders, etc. The reference case we're going to see here, it's not too big, and this is going to explain some of the performance we have afterwards. It's 180 million DOFs. And for CPUs, we're going to look at AMD Genoa CPUs. I didn't talk about GPUs here. The GPU we're going to look at, it's going to be one GPU, it's going to be a H100. The way we usually, if we look at the traditional method algorithm to invert this problem, for each group in red, we would look at each direction in green, and we will sweep all the cells in blue. So we assemble the local system, we assemble the right-hand side, and we do a Gaussian elimination. Now, if we do this, it means that we have very few parallelism to expose on that thing, as I was saying before. Now, what we've done is we've looked at papers which have been written, and we've actually tried to see if we could do different combinations between all these three loops and to see which one is the most interesting for us to expose maximum parallelism. And what we found is that by putting the space problem at the top and putting the energy problem in the inside, we actually managed to factorize some operations out, and also we also managed to expose more parallel opportunities in this case. Just putting the parallel things we could do here, and remember, we are not changing the result. We still have exactly the same results when we change the loops. So we're converging the same number of iterations, etc., etc. The way I'm going to present the results here, we've done a set of calculations, lots of them, and each time I'm going to show a table, except at the end where I'll show you some graphs, where we're going to compare the first implementation, which is a traditional one, and the different upgrades we do to it each time. What we call the grind time in nanosecond, it's the time taken divided by the total number of DOFs. It means that it's the time to produce one DOF, to solve for one DOF, all right? We can see that if we just take the naive traditional implementation and we change it for a problem where we have 4 energy groups, where the first one we will treat each energy group sequentially, and this one we're treating all of the four ones at the same time, we get, just by doing this and nothing else, we just get a first result. We're getting a little speed up. Then what we started doing is, if we look at all the direction in a given, what we call an angle set, we are able to have, we can actually exploit vectorization on those angles. And this is what we've done using the Cocos SIMD types. Well, what I was doing earlier, I used to write code with intrinsics, so it was complicated to port to different platforms and to actually keep it up to date. With the Cocos SIMD types, this simplified our implementation. And in this case, just by doing the SIMD type against the non-SIMD one, we see that we are getting huge performance gain in this case. And then we decided we added more parallel things on the parallelism by looking at the different angle sets in all the 6 direct sextants of the units your circle. And we see that if we have vacuum boundary conditions, we could treat these as independent angle sets too. So we defined the different task granularities here. The most upper course one could be, for one cell, we're going to treat all the groups and all directions for this one. This is what we call a K-task. A KD task is for one cell in one direction, we're treating all the groups, and then we have the most unitary one, which is for one group will create one direction and one cell. The way we are doing this, so we start, like I was saying, if we have two threads in this mesh, we start by processing cell 1, then we can move to 1 and 2 here, and then the front gets to size 3, except that we only have two threads, so we have to do the task for the two, we solve for 1 and 2 again, and we have to wait, so one of the threads will wait, and then we solve for this one, all right? So this is what we've called a front synchronous algorithm in this case, and we move on like this, so on and so forth. So we build, in this case, we build a DAG, and we store it in CSR format. We build one global graph for each of the angle sets we have, and we choose the granularity at runtime, and we see that we can actually do a parallel loop over all the task in a wavefront. By doing this, the best result we had with 128 threads was actually getting a performance gain of 75-76 speed up on this problem. The implementation is simple using this front synchronous algorithm, and it's very efficient when you have large task counts, except that we have global dependencies between the fronts, and we can't exploit the fact that some threads will be waiting while others are still computing, and you could actually use those threads to start doing computation on the other side. So this is where we've used a task-based approach using static task graphs. In this case, we've used the Cocos work graph policy. We've done two things with this. We've done the vanilla Cocos work graph policy, which has an atomic-based queue which is shared by all threads. And then we've also worked a little bit. So the results, I'll show you the results, and I'll show you what we've done afterwards. The results are as good in this case as the synchronous one, but bear in mind that the problem is very small. If we had much bigger problems with the number of groups, etc., which we've seen, we do get better speedups in this case than with the synchronous algorithm. So what we've done, if we look at the work graph policy into details, it has a single work queue shared by all the threads. It has a first-in, first-out structure, and all the accesses to the queue are atomics. Which means that when you push, you have to actually wait before you pop, and you have some contention between the different threads. What we've done with our custom work graph policy, we've put one work queue per thread. We've had a last-in, first-out structure. This way we maximize locality between spatial locality and temporal locality in our problem. And also, we could avoid atomic operations in this case. So the way it happens when a thread has its queue which is empty, it becomes a thief. So we've implemented the work stealing mechanism. It acquires a random victim's queue lock. It tries to steal the victim's queue at the tail, and if it succeeds, it executes the task. So this is what happens here. You're pushing the task number 8 here. We pop it, and then the last one to come was task number 3 here, which is the last one available to be robbed, and the next thread is able to rob it from the worker. We have better locality, and in fact, it was much better to implement it this way, and we had very good performance with what we've done. If we look at the scalability test, this is a strong scalability test. We see that the grind time as a function, which is on the y-axis against the number of threads on the x-axis, is actually dropping as we increase the number of threads from 1 to 128. The first set of results which actually go off, these are the ones which are we're using where we had no parallelism on the angle set. So forget about this one, it's not interesting. But we see that all the different curves, the gray, pink, and brown curves are all going down as we scale with the number of threads in this case. Same thing if we look at the speed up, we see that we get close to ideal speed up. Ideal speed up is, in our case, I did not show it here. We've calculated it to be our ideal speed up for the transport problems. It would be something which we would go. It's not linear, of course. It's going to crumble a little bit afterwards, and we're very close to what we should be expecting in this case. Now, for our GPU implementation, this is very preliminary work. It has been done a few months ago. We're actually working on it. We need to expose more and more parallelism in this thing, so we're going to use the most unitary task we could do, which is for every direction, every cell, every group. We also want to store everything on the GPU memory, so we don't have any communication with the CPU. Since we have everything into Cocos, we don't have to tackle things differently using unified memory or whatever. And also, for solving the problem, each front is solved as a batch assembly problem. So we assemble and we solve it in batch. And for this case, we needed to have efficient batch linear algebra. We didn't use Cocos kernels because in Cocos kernels, we could only do the parallel 4 on the size of the batch, which was very generic, and also on the different. It's also very generic in the size of the matrices it can treat. In our case, we've implemented some optimized kernels, which is the same strategy as the Magma library. And we've been able to use unrolling for different sizes up till matrices of 64 by 64. And for larger matrices, we do some block algorithm on it. These are the results. If we look at the matrix, if we look at the performance in flops as with the size of the matrices on the x-axis, where for each set of curve is actually for a number of, we go from 128 matrices to 130,000 matrices. So we see that we're actually getting good performances. We see where we get to some sizes of the matrices where we're getting out from the warps and the blocks, you actually see performance getting down. And one thing we should have in mind here is that the size of the problem we are looking at, I didn't say this at the beginning, it's a 36 by 36 matrix. And if you look at 36 by 36, we are well within a performance dip here. In this case, we're just after 32 by 32, and this is going to cause some little problem afterwards, but it's not really, it doesn't really matter. So the grind time, as we look here for different matrix sizes, and we look at the grind time for solving, we see that it's actually increasing a little bit as the size of the matrices increase. This is normal. And also, if we look at the performance, the net performance in flops, it's getting higher and higher as the size of the matrices increases. The only offside of this is that since we had a CPU problem which was perfectly vectorized, and for the number of directions we took, which was 16 times 32 gives you exactly 512, which is your AVX12 register. And the GPU problem, we are exactly in a performance dip in the well. In this case, the GPU is actually not as good as the CPU problem. But in most cases, we had one GPU, the flops we are actually getting from one GPU is equal to the flops we're getting from one node with the thread, so which is very good for us. This is very acceptable. So if we look at the bottleneck, this is where it's a bit difficult for us to work on from now on, because we are out of ideas to actually optimize the problem. We are spending more than 65% of our solving time in matrix assembly, which is, okay, assembly time is classical in most problems for GPUs, but here, in this case, we're totally at the mercy of the bandwidth. So and we say it, if we go from V100 to A100 to H100, as the bandwidth increases, we actually get more and more performance. So we have to try to see how to do it differently. For the time being, this is not solved. So my concluding remarks here is we've been able to implement something with Cocos which is actually very good. The performance which we are getting with this code is actually much better than the solvers we have in our legacy codes. And since I know those slides were going to be public, I didn't put a number here, but it's like a 7-8-fold, and where we don't have any preconditioning in this case, and they are preconditioned in their case. So we are very, very happy about this. So if we precondition, we know we're going to get even more speed up. The speed ups are very satisfying considering the small size of the problem. We're going to do much bigger problem sizes, but since actually we are only limited to doing things on one GPU, so we have to work a little bit more. As I was saying, the general case we have here is with one GPU have the same amount of flops as with 128 cores. The next steps for us, this was the first step. The next step for us is testing the multi-GPU implementation, testing what has been done by Roma, with Cocos Graph's implementation on the other side, and also testing more architectures we didn't have time to test on AMD. I think that's all for me. Thank you.
Thank you. Questions, anyone?
How much performance are you expecting to get by using streams, as opposed to using only one?
I didn't hear you. What did you say? How much performance?
Do you expect to gain using multiple streams as opposed to only one?
From what we've seen and from what we have here, if we look at one node where we would have 4 cards, I suppose we could try, thinking about the comps and everything, I think we could get something around, if we get 2 to 2.5, that would be good for us. We'd be very happy.
Anyone else? Thank you.
Thank you.